All right, proposition 16 says, in any triangle, if one of the sides be produced, the exterior angle is greater than either of the interior and opposite angles. So what that means, and here's the very first line of the proof, is to extend BC, line BC. So here's my triangle ABC, and I'm going to extend BC to just some point D. It doesn't really matter where D is. It's more just for the naming convention that we have a D at all. So the claim is that this angle on the outside here, ACD, is larger than either of the interior and opposite angles, meaning it's larger. ACD is larger than ABC, and ACD is also larger than CAB, so the interior and opposite angles. And probably, you know, just from what you already know about triangles, or you can probably deduce that in fact angle ACD in Euclidean geometry is equal to exactly the sum of those two angles. Because the sum of those two angles is the supplement of angle ACB, and that's what ACD is. It's the supplement of ACB. So, but in any case, we're not proving that it's equal to the sum of those. We're just saying ACD is greater than either of these. It's larger. Okay. All right, so how do we prove this? It's pretty clever. Yeah, it's pretty clever. So let's see how we do this. So the first thing is we will bisect AC. So first of all, I guess here's proof. Bisect AC at point E is what we'll call it. All right, and then I'll do that. I'll just make a couple of marks here so that I can, rather than making like the full circles that I would normally make, just make a couple of marks so I don't make too messy of a diagram. All right, so connecting these points with, or this point with B gives me, yeah, right there. There's E. Okay, bisect AC at E, and well, how do we know that we can do that? That was proposition 10. Proposition 10 allows us to bisect. And then next, we're going to join BE and produce it to F such that EF equals BE. So join BE, let's see, and is that being... Yeah, it's not justified in here, but, you know, joining BE would be postulate 1. And in particular, we want to extend BE to a point F such that BE equals EF. So maybe I'll make this full circle. It might be pretty. As much of the full circle as possible, at least. I don't want to write through my proof, or draw through my proof. There we go. So now if I just extend, draw BE out to this circle, and where it meets, I'll call that F. I'll draw this whole line here. There we go. So join BE and extend to F such that BE equals EF. Let's see, and yeah, let EF be made equal to BE. So that was proposition 3. Although, again, the way that I just did it is by making a circle. So yeah, BE can be made equal to EF just by making a circle. Center E with radius B, and then seeing where it intersects with BE. But for the rigor, that's proposition 3 that allows us to make BE equal to EF. What comes next? Next, we join FC. And for some strange reason, that one is justified using postulate 1. Seems a little arbitrary to me, but whatever. All right, so join FC. Postulate 1 says we can do that. And next, let AC be drawn through to G. So again, and for some reason, this one also is justified with postulate 2. So it's just saying, just extend AC to some point G. This one, it doesn't really matter how far out it's extended. It's kind of just like a naming convention for us. Give us some points to name. So extend AC to G, which, again, in here, that line, extending AC to G, is justified with postulate 2, but the line of extending, which I guess I didn't write in here, of extending BC to D was not. So maybe I should just write that. Extend BC to D. Yeah, for whatever reason, that extension is not justified with postulate 2, but extending AC to G is justified with postulate 2. It seems arbitrary to me. I don't know. Maybe there is some reason, but in any case, they're both, so simple that it's like, yeah, we can, by proposition 16, we can kind of just be like, yeah, of course we can do that. All right, so next, then, since AE is equal to EC, BE to EF, the angle AEB is equal to FEC because they're vertical angles. So we get proposition 4, side angle side. So let me just write that out. So then AE equals EC. So AE equals EC. This is because E is the midpoint. So this was by construction. Right here on the very first step was E is the midpoint. So AE is equal to EC. What's next? BE is equal to EF. Why is that true? Well, again, that was just by construction. For me, it was they're both radii of the same circle. But as far as the justification goes, we used proposition 3 to construct it that way. So BE is equal to EF. And then the very last thing, angle, at least the very last thing of this step, angle AEB equals angle FEC. So AEB right here, which in mine looks very much like a right triangle. That probably actually is a right triangle, but we don't know that yet based off of what we've found in the elements. So AEB is equal to FEC. And so the reason that these two angles are equal is because they're alternate angles. So that was proposition 15. So what have we shown? AE equals, I probably should have said CE just to keep things in the same order. EB or BE is equal to EF, and then these angles between those equal lines are also equal. So by side angle side, we have two congruent triangles. And whenever Euclid cites proposition 4, he cites the whole thing, which was kind of long, if you remember, but I'll just say it this way. So angle AEB, or sorry, not angle, but triangle AEB equals triangle CEF. And this is by side angle side, or proposition 4. So AEB is this triangle right here, is congruent to CEF, this triangle right here. So, in particular, we have that angle BAE is equal to angle ECF. BAE equals ECF. I guess I have them a little bit backwards, or maybe Euclid has them a little bit rearranged. Doesn't matter. The idea is the same. because of their corresponding angles in the triangles, in the congruent triangles. But, he says, but angle ECD is greater than angle ECF. And this is justified with common notion 5. The whole is greater than the parts. I think that just for the sake of clarity, I think that maybe there should be, let's see, is this the step? Let me see here. It might be the next step, actually, where I felt like it was not totally clear. So ECD is right here. Yeah, is greater than ECF. This is, again, one of those places where Euclid just kind of says this, and it's like, well, it should be obvious, look at the picture, look at the diagram. I think if you wanted to be really rigorous about it, you could say something like, well, note that angle ECD is equal to angle ECF plus FCD. Therefore, by common notion 5, ECD is greater than ECF. But Euclid didn't feel the need to write all of that out and be so verbose. So in any case, ECD is larger than ECF. Okay, great. And next he says, therefore, angle ACD is greater than angle BAE. And he just states this. Right, and this was the step where I sort of felt like, when I was reading through it earlier, I kind of took pause. So ACD is right here. ACD is greater than angle BAE. What? How did he get that? Maybe if you want to, just take half a second, pause the video here, and and see if you can prove this line to be true, just off of everything that we've sort of stated and proved so far. Can you prove that to be true? Angle ACD is greater than angle BAE, if you want the little challenge. Otherwise, here's how I kind of reasoned my way through it. So I'll put it as like a little note here, because this isn't actually in the Heath translation. It's just something that I think it makes sense to add in. Okay, so we'll look first at angle ACD. Angle ACD is the same angle as angle ECD, since E lies on AC. So angle ACD is equal to angle ECD. Okay, great. And we just found, and we kind of just discussed why this is true, that angle ECD is greater than ECF. So angle ECD is greater than angle ECF. Well, we also know, what do we know about angle ECF? Well, ECF is equal to, let's see, it wasn't that line. Right here, this was the line. Angle ECF is equal to angle BAE. Equals angle BAE. And that is the proof right there, because we're saying here there's like this inequality in the middle and then equalities on either side. So angle ACD is greater than angle BAE. And let's look at that in the diagram. So here's ACD right here. It's that external angle that we've been looking at. Angle BAE is this top internal angle. So BAE is the same as angle BAC. So that's what we needed to prove. At least that's part of what we needed to prove, because we need to prove also that ACD is larger than angle ABC over here. And here, let me just read what it says in the translation. It says, similarly also, if BC be bisected, the angle BCG, that is the angle ACD, which we can say that BCG and ACD are the same because they're alternate angles, ACD can be proved greater than the angle ABC as well. Let's see here. Yeah, yep. So ACD is greater than ABC. So it's basically what I read out of that is he's saying, hey, do this exact same procedure, but instead of cutting this line through AC, cut it down through BC. So bisect BC and then extend this line out. Maybe you'd call that H or something. Extend AH so that AH equals HJ or whatever you like. You probably have to connect J and B would be my guess, and then you can get some congruent triangles again, and the same argument falls out. But anyways, I'll just say by a symmetric argument. Maybe I shouldn't say symmetric. I think symmetric works here. By a symmetric argument, we can show that angle ACD is also greater than angle ABC. And that's what we came here to show. So, QED, therefore, etc.